Okay, so our start cost, see, I've got that on there now. Right, our start cost is 0. All the other nodes need to be put in as a cost of infinity. How many times can one person put infinity on a sheet? Right, so we look at our neighbours. So we pick that cheap cost. So the cheapest one at the minute is A. So we close it straight away, pick it up, and then we're just going to do each of the neighbours. So it's got a neighbour C that costs 0 plus 2. So we're going to put the cost down as 2, and remember to put the parent in. If you forget to put the parent in, it'll break everything. We've got another neighbour B that's going to cost 4 to get to, and that's parent A. And then we've got another neighbour E that's going to cost 3. So that's better than infinity, so we write that down and write A. So that's our first loop, and that's it. So we go again, pick the next cheapest cost. So the cheapest of the open ones now is C, which is 2. So we pick it, close it off straight away. Look at its neighbours. C's got a neighbour A, but that's in the closed set, so we ignore it. Okay, you can't see my hand gesticulation, can you, when I'm doing this? And I'm screen capturing. It's a bit of a shame, but there you go. You're missing out, those people who are watching this video, but there you go. Right, it's got another neighbour D, but this time it costs 4. But we need to know what the total cost of D is. So that is whatever C cost, which was 2, plus the 4. So that makes it 6. It's better than infinity, though. So we're going to write that down. The parent for that cost is C. There are no other neighbours, so let's do another iteration. So we're going to go look through. We've got a 4, a 6, and a 3. Oh, E's going to get picked then. So we're going to pick E because it's the cheapest. Let's look at the neighbours. There's quite a few. It's got a neighbour A, but that's closed, so we're going to ignore that. It's got a neighbour B, so let's have a look at that one. It's cost me 3 to get to E, and it's going to cost me a further 2, so it's going to cost me 5 to get to B. It's not cheaper. We've already found a cheaper route, so we don't have to update anything. We've got a new neighbour, though, G. So we've got 3 plus 2 is 5, so it's going to cost me 5 to get to G. 5's better than infinity, and that was parent E. No more neighbours. So let's go through the iteration again. So we've got 4, a 6, and a 5. So it's going to be B we pick this time. Close it off. Look at its neighbours. Neighbour A, already visited. Neighbour E, we've already visited. Right, neighbour D. Let's have a look at that one. So it's cost me 4 to get to B, and it's going to cost me a further 1. So that's 5. Oh, that is better than the current cost. So we're going to update that, and we're going to say, right, there is a better way of getting to D, and that is via B. So we update the parent. Another neighbour is F. That's got infinity, so this is going to be updated because it's better. So we've got 4 plus 7, plus 3 gives us 7, and that was parent B. No more neighbours. So let's do another iteration. Let's look for the smallest. So we've got 5, 7, and 5. We've got 2 5s. Just pick the first one. Doesn't matter. Okay. So we're going to pick D. If you picked G, it just means you just build the table slightly differently. You will still find the optimal route. So it doesn't matter. So let's just pick, shall I pick G just to spice it up? Let's pick G. Okay. Look at the neighbours of G. So we've got E. Close, so I don't have to do anything. We've got F. So there's only 2 neighbours here. Right, let's have a look at the calculation. So it cost me 5 to get to G, a further 1 to get to F. Ooh, that's better than 7. So I'm going to update. And that was coming from not B, but G. No more neighbours, so I'm finished. So I'm going to go around and iterate again. So I've got a 5 and a 6 and a couple of infinities, so they're going to get ignored. Now I'm going to pick that 5 up. So I'll close it off, the D. Look at my neighbours. C's a neighbour, but it's closed, so I don't have to do anything. B's a neighbour. Ooh, it's closed, don't have to do anything. F's a neighbour. Ooh, not closed yet, so let's have a look. So it cost me 5 to get to D, plus a further 2 to get to F. That's going to be 7, so that's not going to be better. All right, so it doesn't matter what order I pick those 2 5s in, because as long as I don't be stupid and overwrite a number, and there's an easy way of checking, these numbers should always be decreasing. If it suddenly goes up again, if I'd have gone like that, Oh, this has been doing this like mad today. I've got to now find that. Let's zoom out. Gotta love computers. I've no idea where I've been drawing that. No, it's there. Right. If you end up writing a sequence of numbers like that, then you know you've gone wrong because you've just increased. So you've written it down wrong. So give yourself some double check on that. Right, okay, so we've done D. Let's do another iteration. So we've got currently open, we've got 6 and a couple of infinities. So it's automatically going to be F we pick. Arrgh. Oh, God. I don't know why it keeps doing that. Now I can't find it. Oh, this is going to get on my nerves. Right, so I pick the F. Right, neighbours. So we've got a neighbour B, closed. We've got a neighbour D, closed. We've got a neighbour G, closed. We have got a new neighbour, L. So it cost me 6 to get to F. It's going to be a further 1 to get to L. So that's 7. So I'm going to put F. Right, no more neighbours. Iterate again. Infinity and 7, it's going to be the L that I pick. So I'll look for my neighbours. I've got a neighbour F, but that's in the close set, so I ignore. But I have got this neighbour K. So let's explore that one. So we've got, it cost me 7 to get to L, plus a further 6, that's 13. Better than infinity, so I'm going to write that down. K is my goal, but I haven't visited it, so do not say I can stop. All I've done is I've just done a costing. I haven't been there. We only stop when we've been there. So let's iterate again. There's only one thing left, so it wouldn't be a very long search, but we pick up the K. That's the one we want to get to. So that's when we stop. Okay, so we've now completed our table and we can now work the route out. But we must make sure that we go backwards. So we're going to start by writing K down and then we're going to say, right, where did I come from? So I look at the parent L. Where did L come from? So I look at the parent and the parent is tracking what was the cheapest node to that. So F is the cheap one for that. Where did F come from? G. Where did G come from? G was E. So I'm not trying to look at the diagram at all. I'm looking at the table of data I've made. E came from A. Where did A come from? Null. Null is our indicator that that was the start. So that is my route. A, E, G, F, L, K. Bit of a route. But remember, these numbers aren't necessarily geographical. All right? They just represent a cost of travel, whatever that cost is. Could be anything. Could be time, could be distance. It could be electrical resistance if you do map using a graph to do resistor networks. It could be speeds, you know, so it could be available bandwidth on a connection between two routers, which would be interesting because you'd have to look for the biggest, wouldn't you? You'd like flip it on its head. You'd be looking for the biggest cost. If you were saying these were the, you know, if A to C was 2 terabits per second, A to B was 4 terabits, so you'd favour the bigger one. So you could switch it on its head. So we just go for cheapest, is what we tend to do. But it doesn't have to represent the cheapest. It could be the most expensive. Okay. If you were trying to work out, I don't know, the production process of a product and you wanted to maximise how much money you were going to get at the end, you might look for what are the most expensive things. I don't know. Okay. Right. Let's stop.